Hello everybody! This is another video on exponentials and logarithms to go with your actual physical notes. So it's pure chapter 14.7, the 7th lesson on exponentials and logs. So we're going to have a look at how exponentials and logs are one and an inverse of each other and apply that to e to the power x and the natural log of x. So before we get into that, first of all, as ever, there's going to be a warm-up. So here's three questions for you to try, 1, 2 and 3. So pause the video and try them yourselves. When you're ready to see the answers, press play and just make sure that you've got the same solutions as me. Okay, so here we go. These are the solutions to question 1. So for question 1a, we need to complete the table of values for x squared and the square root of x, rounding answers to one decimal place where we need. So first of all, when x is 0, obviously we know that 0 squared is 0, and also that the square root of 0 would be 0. Likewise, when x is 1, really easy, 1 squared is 1, the square root of 1 is 1. When x is 2, the square of 2 is 4, and the square root of 2 is about 1.41. Check on your calculator if you need. So to one decimal place, this is going to be 1.4. Now we've got these table of values, we're going to now plot f of x and g of x. Now, I hope you'll forgive me, but I've been getting rather annoyed with my awful plotting, so I've sort of cheated here and just done these using a graphing piece of software. So for 1b, you should have got these sorts of plots. So f of x I've done in red, that's x squared, and in blue is the graph of the square root of x. So thinking of this now, going on to part C, using algebra, we need to show that f and g intersect at the points 0, 0 and 1, 1. So they'll intersect when f of x is equal to g of x, quite obviously. So I'm just going to write that down. They'll intersect when f of x is the same as g of x. So in other words, they'll intersect when x squared is the same as root x. So we need to set x squared equal to root x. What we can do now is you can square both sides of this equation. So square x squared, that becomes x to the power 4. And if we square the square root of x, that'll just give us x. We can now rearrange this so it's all on the same side of the equation. So just give myself a bit more space so I don't have to scroll down the page. We can say this is the same as x to the power 4 minus x equals 0. And this will now factorise. We can factorise out an x on the left-hand side. So then we get x brackets x cubed minus 1 equals 0. So this is going to be equal to 0 when x is equal to 0, or x cubed is equal to 1. So in other words, when x is 0, and when x is 0, x squared will be 0 times 0, which is 0. So therefore that would make y equal to 0 as well. Or if x cubed is 1, 1 times 1 times 1 is 1, so that's the same as saying x is 1. So or x is 1, and therefore substituting into either function, that would give that y would have to be 1 as well. In other words, they intersect at 0, 0 and 1, 1. For part D, we need to think about the equation of the line of symmetry of the curves f and g. Well, if you have a look here, this is above the line y equals x, and the red line is below the line y equals x, between 0 and 1. And if you imagine this here, you can hopefully see that there's a line of symmetry directly between these curves, and the line of symmetry actually would go perfectly between them and would in fact be the line y equals x. So the line of symmetry is this line here going directly between them, which I'm hoping you can see here. So that's for line y equals x. And in fact, what you'll see in year 13 a lot is when we plot the graphs of a function and its inverse, the line of symmetry between the two will always be the line y equals x. So that's question 1 completed. Question 2, we've got these same functions from question 1. So finding in terms of f of root x. So here the input for the function f is root x. Here you can see whatever the input is, we square it. And so in this case, we're going to be squaring the input, which is root x. Root x all squared, obviously, just gives us x. Likewise, g of x squared, whatever the input for g is, it gets square rooted. And so here, we're going to be square rooting x squared. Squaring and square rooting are inverse functions, so again, we get back the original x. Question 3, Calculus Corner. Show that the area of a finite region bounded between the x-axis and the curve y equals x cubed minus x is 0.5 square units. So what we should do for this one is have a seat and think about if this will factorize or not, and of course it will. So y equals x cubed minus x. We can factorize out an x from here, which gives us x squared minus 1, and that will factorize again, because x squared minus 1 is a difference of 2 squares. So then we'd have x plus 1, x minus 1. And so if we were to graph this, by graph I just mean do a sketch, it's a cubic, a positive cubic, so it's going to have the S shape going upwards. And it's going to have intercepts at 0, minus 1, and 1. So the shape of it is going to be something like this. Down and up again. So here we have minus 1, crosses at the origin and again goes through the x-axis at 1. And so the finite region bounded between the x-axis and the curve is going to be this section here, and as well as that is also going to be this section down here. Now, forgiving my awful sketch, I can't sketch for toffee, you might hopefully consider that there will be some symmetry with this graph, and in fact maybe this area is the same as this area over here. Anyway, what you should have learned from the previous chapter is when we integrate a function between limits, that tells us the area in between the curve and the x-axis. It tells us the area underneath the curve. And so the total area here, that region plus that region, the area bounded is going to be the integral of the function with respect to x between the limits. So this limit here, we need to integrate separately as well. This region here, we need to think about separately to this region. Remember, when we integrate a curve which is going below the x-axis, that will give us a negative area. And so if we call this A and that B, region A is between minus 1 and 0. So between the limits of minus 1 and 0, we integrate the function x cubed minus x dx. And then we add on region B, which is from 1 to 0. And it's still the same function, it's still x cubed minus x with respect to x. However, knowing and predicting that this will give us a negative area, what we need to do is find the magnitude of this. So we're not interested in the minus sign, we're just interested in the absolute size of this bit here. So if we integrate this, I'll just say here as well that this is region A, and this is region B. So remember, when we integrate, we take the power of the variable, take it up 1, and then divide through by that new power. So x cubed becomes x to the power 4, and we then divide through by that 4, so we get a quarter x to the power 4, and the x becomes x squared, and we divide through by the 2, so we get minus a half x squared, because that was minus an x to begin with, in between the limits of 0 and minus 1. And then we add on, again, the absolute size of this, which is the same function. So it's going to be a quarter x to the power 4 minus a half of x squared between the limits of 1 and 0. But again, remembering, we just want the size of that, the absolute size. So, for region A, first of all, I'll show you how to cheat and do this on the calculator in a second, so don't worry if you're thinking, how can the class whiz save my bacon? I'll show you how. So, for example here, we're going to have, we input 0 first of all, the upper limit. Input 0 into this, the whole thing's just 0. Then minus off what we get where we input minus 1. Well, minus 1 to the power 4 is just going to give us 1, so it'll just become a quarter. Then minus a half of x squared. A half of minus 1 all squared is just a half. And we plus this bit here. So when we input 1, 1 to the power 4 is just 1, so that's a quarter times 1, which is a quarter. Then minus a half times 1 squared, which is just a half, so a quarter minus a half. Then we subtract off what we input when we put the lower limit in. But the lower limit is 0, so this whole thing just becomes 0. And as you can see, if we didn't take the absolute magnitude of this, a quarter minus a half, that would give us a negative area, which is obviously not what we're after, which is why we take this magnitude here. So now if we input this, what we're going to get here is 0 minus a quarter minus a half is minus a quarter. So minus a quarter, the first bit is going to give us 1 quarter. Now we look at the other bit now. So over here, we can have plus the size of a quarter minus a half. Well, a quarter minus a half takes us down to minus a quarter. So the size of minus a quarter is a quarter. That minus 0 is not going to do anything. So a quarter plus a quarter gives us a half, which is 0.5. So we've just proven here that that's equal to 0.5 units squared. So, moving on to the main bit of the lesson, the natural logarithm. So, a few details. The natural logarithm of a number, x, is the logarithm to the base e of that number. So, if we have e to the y equals x, that's the same as saying it's log base e of x is the same as y. Now, log base e itself is often written as ln, as in log natural. So if you've got a log with a base e, that's ln. And the good thing about this is, with a calculator, we don't need to put in log base e. We can just press the ln button, which we have here, followed by the value of which we want to find the natural log of. And a bit more about this. If we now have a graph where this is obviously the y-axis and this is the x-axis, we can see how the graph of y equals e to the x compares with the graph of y equals ln x. So first of all, I'm just going to show you what y equals x looks like. Obviously, just a straight line. Then y equals e to the x is going to go up very, very fast as such. And now, the graph of y equals ln x is a reflection in the line y equals x of e to the x. And so this is because e to the x and ln x are inverses of each other. In the same way that powers and logs are the inverses of each other, this is just a special case of that relationship. So we need to think about these expressions here. These are special cases of the natural log. And so what I'm going to do just to remind us is just going back to the previous slide or two we've got these relationships here. So if e to the y equals x, that's the same as saying ln of x is equal to y. And so looking at this first one here, e to the ln x, well, if we've said that ln x is the same as y, that's the same as e to the y, but e to the y equals x. And so if we take e to the power ln x, that gives us just x, because if we take e to the power of something and then do the natural log of it, that's doing the inverse of the inverse, so it undoes each other. To the power of e and log to the base e, they're both inverses of each other, and so we just get back the thing we were trying to find the natural log of in the first place. Next we need to consider ln e to the x, and so from ln e to the x, what we could do with reminding ourselves of is a lesson from a previous session. So if I just go forward here and show you what we discovered from a previous lesson, we had a power law, and so the power law, I'm just going to write in here this is equal to x again. The power law, if we take a log base a, and then what we're taking the log of is in itself a power, we can consider this power as moving to the front and multiplying the log of just the thing without the power. And so this x we can bring to the front. So ln e to the x is essentially the same thing as x to the ln e which will just be x, because ln e, the log base e of itself, is just going to be 1. So I've given the game away here now. So ln e is going to be equal to 1. So what we've got here, that's equal to 1, that's equal to x, as is e to the ln x. So now let's solve some equations. I'm going to show you a different method, a more standard method for solving equations to do with logs and natural logs. So here we have e to the x equals 3. What we can do with equations, just going back to the general idea from maybe even primary school for some of you, what you do to one side you can do to the other, we can do what we call taking logs of both sides. So because this is e, we can do ln of both sides. So ln e to the x equals ln 3. But from what we discovered previously, this is the same as x ln e, which is just going to be x, because ln of e is 1. So I'll put that extra step in for you until you get used to this. So x ln e equals ln 3. But just remind ourselves that ln of e is just going to be 1. So x times 1 is just x. So in exact form, x is just ln of 3. In the same way as we can take logs of both sides, we can also exponentiate both sides. So we can put both of these here for part b to the power of something. Because we're talking about natural logs, the most natural power is e itself. So e to the ln x equals e to the power 3. But going back to what we just mentioned a couple of moments ago, e to the power of ln x is the same as x itself. So therefore we just get that x equals e to the power 3. Here for this one we can take logs of both sides yet again. And so ln e to the 2x plus 1, that is slightly wonky, that equals ln 3. Now we can bring this power to the front, so we just get 2x plus 1 multiplied by ln e, but ln e is just 1, so we don't need to include that really. So that gives us ln 3. We can now rearrange this as we would any equation. So 2x equals ln 3 minus 1. Then divide through by 2, we get that x equals ln 3 minus 1 all over 2, or we can just say it's a half of ln 3 minus 1. Either or, doesn't particularly matter. Moving on to another couple of worked examples now. So we need to solve this equation here first of all. So we've got 2 lnx plus 1 equals 5. We can subtract 1 from both sides first of all. That gives us 2 lnx equals 4. Half both sides of the equation to give lnx equals 2. We can now do both of these to the power e. So e to the lnx equals e to the power 2. But of course, e to the lnx, the ln and the e undo one another, so we just get left with x. So in exact form, x is e squared. Part B is a bit of a throwback to the other day, where we talked about hidden quadratics. And so what I'm going to say is we can let big X equal e to the x. The equation would then become e to the 2x is e to the x times itself, so that's x squared, big X squared I mean, plus 5 lots of x equals 14. We can rearrange this to a standard quadratic form, so the squared term, the single x term and the constant are all on the same side, so we get this. This will now factorise out. So we need to find two numbers that multiply to give minus 14 and add to give 5. Well, those numbers are positive 7 and minus 2. So we can split this 5x into a positive 7 and a minus 2. And now these four terms will factorise into two nice brackets. So this bit here, x squared plus 7x, we can factorise out an x, and we get x plus 7. Then the minus 2x minus 14 part, if I factorise out a minus 2, we get x plus 7 again. So that bracket x plus 7 duplicates. So we've got x lots of it over here, minus 2 lots of that bracket over here. So in total we have x minus 2 lots of x plus 7 equals 0. So therefore what we get is that either big X is 2 to make this bracket equal to 0, or, of course, we might have that big X is negative 7. But the equation wasn't in terms of big X, was it? It was in terms of little x. So now we need to remind ourselves what big X was. Big X was e to the power x. And so either e to the power x is 2, or maybe e to the power x is minus 7. Well, can that ever be the case? Well, it can't. E is a positive number. A positive number to any power can never yield a negative value. And so we just need to say, well, that just can't happen. And so we're left with the one solution where e to the x equals 2. So if we then take natural log of both sides, we get ln e to the x equals ln 2, but of course ln e to the x is just the same as x itself. So therefore, in other words, x equals the natural log of 2. So now as ever, everybody, it's over to you to try some. So here's the suggested exercises on page 327. It's 14G in the blue algebra book. Just try questions 1 to 6. Work through them all diligently. Check your answers at the back. If you've made a mistake, try and see where you've gone wrong. If you're still unsure, please do drop me an email or leave me a question or a comment in the comment section of this video. Again, thanks for listening. Do keep working hard, and you'll hear from me again in the next video, or maybe on an email. Thanks for listening, and be in touch. Cheers.